Kia ora, folks. I just want to talk about the physics of interference. And so this model I've got here is, a double slit, basically a tiny little slide with, two little gaps. And the distance between these two gaps is tiny. It's like 0.1 of a millimeter, so 1/10 of a millimeter. And then in front of this double slit, which has got a light source behind it, and it's monochromatic light, meaning the same wavelength, is a screen. And the distance between from the screen to this double slit could be 6 to 7 meters. So quite a difference between the measurement of D and L. So what I want to show you here is that what happens at these points along the screen, because if you were to look at the screen, this is a light model, so if you were to look at the screen, you'd actually see patterns occurring along the screen. So in this particular position here, you'd see a very bright, what we call fringe. And in physics terms, we call this an antinode. And this is where n equals 0. And I'll tell you the reason why n equals 0 is that the path difference, if we was to count the number of crests along and say the orange wave is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, if I was to do that, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, the crest is meeting the crest of the other one. So therefore there's no path difference. So PD, path difference, is equal to 0. But if I move this up a bit, these are on two pivots. If I move these waves up, you can see in this zone here, just coming up to this zone, the crest of the blue wave is meeting the trough of the orange wave. And this is where we get destructive interference. So this is where it's the opposite to constructive interference. So no light will be seen there, basically darkness. And in this particular case, the path difference between these two waves is of half a wavelength, so half of lambda. If I go up a little bit further, and not much, but just move these waves up a little bit further, you can see now in this position, the crest of the orange is meeting the crest of the blue. And in this particular case, we're going to get n equals 1 here, and constructive interference, okay, and a path difference of 1 wavelength. The same thing occurs below the principal axis, is just the same as the above. Here we've got destructive interference, a crest meeting a trough, and a path difference of half a wavelength, and then going down further, a little bit further. It's not quite perfect, but you can soon see that the crest of the blue is meeting the crest of the orange. And let's just check that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 blue crests. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 orange crests. So the difference there is 1 wavelength. So hope you understand that. Basically we're talking about path difference there. And I've got another little transparency that I'll just add on to this, and you'll see that that's what's happening. I'll just move this up, and you'll see that the pattern emerges. So here at the central, right on the principal axis, you'll see a central bright fringe. A little bit further up, that path difference is half a wavelength and no light forming. The first bright fringe will occur there, and the path difference will be 1 wavelength, and so on. And the same thing happens below the principal axis. So I hope that's clear for you. I've made another transparency, and this time we're not looking at the waves side on, we're looking at the wave. It's like a little bit like a ripple tank, a wave tank. We're looking down at the waves, and here we've got the crest of the waves is green, the top of the waves, and the bottom of the waves, the troughs of the waves, is red, orangey red. We've got the same slit here, double slit, so two gaps, and we've got a source, one source making waves. So the first pattern that we see coming out of this bottom slit here, we'll see the waves coming out, and this is the wavelength. From any point on a wave from one to the consecutive point is the wavelength. So that's that one there. And if I put on the other transparency, you'll see the other formation of patterns. And you can see there are zones. So you can see red meeting red here, green meeting green here. And if I put on a third transparency, this should really help you understand, is that where the green meeting green and red meeting red, this is where we're getting an antinode, so constructive interference. You can see here, constructive interference. So these are all, and this is called antinode. So yeah, red meeting red, green meeting red. But in the opposite case, you're getting a dark pattern here, a dark zone here, and this is where a trough meets a crest, a red meets a green, or a green meets a red, and the same thing here. So with any kind of pattern like this, you'll see regular fringes, constructive interference where there's the bright fringes, and destructive interference where you're getting no light whatsoever. And this is what we call the nodes here, nodes there, antinodes where you're getting constructive. So I hope that helps. So just having a quick look at the mathematics of the physics interference. This is the screen. This is the double slit. You can see I've got like a bulb here which is emitting a monochromatic light, and we've got a source of light coming out of this gap here, this slit, and a source of light we call S2 coming out of there, and the distance between those two slits is D, and L, big L, is the length between the double slit and the screen. And if I was just looking at the principal axis here now, this will be equal to 0. So that's going to be your first, what we call first bright fringe there. But if I was to choose a point here, and this point here is n equals 1, and we'll call this point P, so this point P, if I was to draw a line from S2, so going up to P there, and I was to draw another line going from S1 going up to P, there is a path difference, and I talked a little bit about this. So path difference is equal to S1P minus S2P. This is absolute, of course. So the difference between the distances is the path difference. And in the earlier explanation, this is equal to n times the wavelength. It's a whole number, and n is equal to 0, 1, 2, 3, etc. Okay, so that's really important to know. So path difference, PD, is equal to n times lambda, which is the wavelength, and this is what we call any constructive interference. Now, if I have a look at this angle here, if I was to draw a line down here, and this is perpendicular, 90 degrees, this is the path difference. This tiny little distance here is the path difference between this ray, or this distance between S1P and between S2P is that path difference. And I know that path difference is equal to d sine theta. just simple trig, sine of theta is equal to PD divided by D, or PD equals D sine theta. So that's important to know. And we also know that the tan of the theta is very similar to the sine of the theta, because the angles are very small. If you were to take the angle, like at 1 degree to 10 degrees, if you sine that, it's very similar to the tan of that same angle. So basically, sine of theta is equal to PD divided by D, and that tan of theta, and if I was to take, I was just going to show you this, that is actually equal to the distance here between this fringe here to the next one, which we'll call x, divided by L. And that is equal to x over L. So here we've got another formula that we can use, is that the PD is actually equal to dx over L. Okay? So d, just to make it simple, d sine of theta is equal to dx over L, which is equal to m lambda. So I hope that helps. And this, just remember, this is for constructive interference. Just in terms of destructive interference, then of course you would want d sine of theta is equal to n minus a half lambda, which is equal to dx over L. So because of course we're wanting integers of half the wavelength, and of course n is equal to 0, 1, 2, 3, etc. And this is what we call destructive interference. And these two formulas will solve every interference problem you have. Thanks very much.